exactly what they're going through. That's a good idea. I'm looking at that, not directly in interaction, but in the clumpy galaxy showed very quickly before, because you have a lot of star formation activity, you have a lot of outflows, and at some point you see clouds leaving the disk.
You're back on.
And okay, maybe this happened like 20 times and you just noticed twice.
No, I spotted that.
Okay. In principle, yes, it's feasible if you do the simulation. At least the simulation that I'm doing shows that it's not that easy. So quantitatively, it doesn't work. I'm not quite sure why. Maybe because feedback is not efficient enough. Either because of the implementation of feedback that I'm using, or just the physics. The feedback that I'm using is kind of, it's not complete, but at least the energy that I put in is kind of okay. So I would not say it's a numerical problem, or it's a simulation problem. But anyway, we are very, very far from getting that. So forming globular clusters above or below the plane of the disk from interaction, from feedback inside the disk, I think it's very difficult. The other point is that when you do that, when you launch your cloud, basically you're going to destroy your cloud, because you enter the hot corona. It's not so dense gas, but you have ram pressure. The thing is moving super fast. So it will you will lose a lot of gas, and maybe it will be kind of difficult to eject something massive enough to form a globular cluster. If you want an object of 10 to the, say, let's be generous, let's say 10 to the 5 solar masses of stars, you need a cloud of 10 to the 6, 10 to the 7 solar masses of stars. That's huge already. We don't have any things like that in this, basically. So you need to start something. So it's probably easier at higher redshift when you have this clumpy structure. But still, you need to send that. You need at least 10 to the 7 solar masses to arrive at high latitude. So it needs to start with even more in the disk. So you need this to exist, and you need something to eject this kind of object. And supernovae, or feedback in general, I don't think it's really it can do that. I think it will just strip the outer part of the cloud. Maybe the center will remain, maybe not. And what could do this effect is just gravitational interaction. If you have two objects like that and they are not perfectly aligned, you could slingshot one, and that would go above or below the plane of the disk. So that was mainly the idea that I had. Doesn't seem to work either, maybe because my disks are too thin. So that could be a technical, simulation issue. If you're looking at a cosmological setup with much more turbulent and thicker disks, that might work. So it has been proposed that it could work to explain the formation of, the existence of globular clusters at high and low latitudes above and below the plane of the disk. It seems more, to me, that's just speculative, but I think it's much more likely that these things come from elsewhere. And they have been brought to the galaxy. They have different orbits, can be a kind of inclined with respect to the galactic disk, they have huge eccentricities. So to probe that, you need everything that Gaia will provide us in a few weeks. Proper motion, chemistry, blah, 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 blah. But it might not be, the conclusion there. I think we really have to go through simulations in the cosmological context. So that would be extremely painful. I know, because I'm trying. That would be extremely painful to have this huge range of scales and time scales between all the steps in galactic formation. Because I think you do need mergers, you do need accretion of gas, you do need formation of structure, etc., to see where these globular clusters are coming from. And it might be that there is not only one channel of formation, and also that the main channel formation is just evolving through redshift, that you go first through this kind of process that you are mentioning. I think it's difficult, but maybe it's possible in extreme environments, and then later you have more mergers, later you have more accretion of satellites or things like that. But the problem, I think the main problem with globular cluster is that it's not like you want to send an object up there. You want to send a huge clump of stars It's not something like the Pleiades, right? It's 10 to the 5, 10 to the 6 solar masses. That's really huge. So if you want to form it there, to form it in situ, you have to send an even bigger amount of gas, of dense gas that remain bound and that will collapse. So it's difficult. But it's definitely the kind of idea people are pushing in nowadays, right? It's
Well, you mentioned cosmology, you meant about dark matter or something else?
well, my definition of cosmology is rather broad. It's the whole galaxy formation thing. So when I say cosmology, it's because most of these studies are based on the cosmic microwave backgrounds from cosmological principles. When you see the entire build-up of galaxy from scratch, and you see them accreting gas, accreting dark matter, accreting gas, etc. So if you just do simulations or theory with dark matter, you will miss a lot of things. And we were discussing about that at lunch. People are claiming that a lot of issues in cosmology, it's just because they used a simulation without baryons, without feedback, without things like that, or this core missing satellite and whatever problem. It's just that your simulation is incomplete, so don't say it's a problem. I mean, it's your problem. But if we want to study galaxy formation, star formation, we need what I call the cosmological context. So maybe it's better to say large-scale structure, long time-scale evolution, the full galaxy formation process with the diversity of environment we have to go through, accretion of dark matter, accretion of gas, interaction with major merger, minor merger, accretion of satellites, etc. And that's the only way you can have the broad spectrum of environment, of star-forming episode and star-forming environment. And I think that's one way to see if star formation is really universal or not. Because if you're only probing one specific environment, you will say, yes, of course it's universal. Now, if you're putting things in a broader context, it might not be so clear. Or maybe it is. I don't know. If it is, it's probably coming from something at small scale which erases all these differences. Like Hurley feedback or stuff like that. Like makes all the core mass function being universal, the MF being universal. But if you look at high redshift, it's really, it's very difficult to think that yes, it works exactly the same as in the solar neighborhood right now. Things are so different. So if indeed they are the same, that means that you need something at small scale to erase all the differences, to get rid of everything. And what is this? The problem, if you want to answer this question, is that you need large scales and tiny scales at the same time, at the same simulation, for example. And that's difficult.
I suppose you have the metal enrichment from galaxies to constrain what the integrated history of the supernova events.
You can look at that. You can have look at the spectrum to derive the star formation histories, to more or less time the merger, because the merger events are linked to star formation activities most of the time. And you can try to reconstruct histories of individual galaxies, but again you have the problem of the mixing in the merger remnant. If you see a peak of star formation, you don't know if the peak is representative of an entire galaxy or only part of the galaxy. And from what I've heard, it's really not my field. Again, Pierre knows much better about that. But from what I've heard, it's really poorly constrained observationally because it's really degenerated.
It'd be interesting to see whether he could say something about satellite disk interactions that would trigger maybe a local burst of star formation on one side of the galaxy, which would then take time to phase mixed. And
why on one side?
Because the satellite goes through the disk.
Ah, okay, on one spot.
That's right, in one spot. It cannot be on both sides at the same time. So maybe it can. You see what I mean? That there's this issue of mixing.
In the stream, we've been compressed by.
Right,
yeah, why not?
Exactly.
Or shocked.
Well, I guess it's one aspect of.
Yeah, but it's mostly stellar, right? It's not really gaseous. You have some gas, but really low density, so even if you can compress it, it might not be star forming.
Right. I suppose it depends on the parameters of your configuration.
Yeah. Because all this is astronomic.
Because the likelihood is that the satellite would hit on the outskirts of it. Yeah.
So yeah, that's also the issue of this problem. You have so many cases with different impact parameters, relative velocities, orbit inclination, and things like that, that it's super difficult to conclude. And making one simulation with, do I dare saying it, decent physics, which means people would accept it's okay to neglect the rest in 2016, which is very arbitrary, of course. But if you do simulation like that, you can make one or two within a few months, because it's huge, you have a huge dynamical range, and you need a huge resolution, so it's very, very costly. And that's just representative of one specific case. And then you have to explore the full range of parameters. So people have been doing that for interacting galaxies. There is the Galmer projects. They made, I think, 1,000 something simulations of interacting galaxies with many, many different parameters. They change the mass, the orbit, the spin-orbit coupling, the relative velocity, all this stuff. They played with that. But if you do that, you cannot go to very high resolution. So still, it's super nice to see the structure properties. So for example, if you want to look at how long you see kinematical signature, you can use this type of data. You don't need much more. But if you are more interested in star formation, in the details of how the gas, how the interstellar medium is, that you need higher resolution. So this means that you have to decrease the size of your sample, and that's difficult.
Cool.
So it's I think it's like every way in astronomy you have to choose between a huge sample but a poor resolution in simulation or in the observations, or one specific what we call pet objects. In observation, you really focus on this one, you know this one very, very well, but you have no idea how representative it is of the diversity of things.
So maybe Thursday we can explore this Gamma library. It's something we could do.
Okay,
Yeah. In the afternoon, a short session on that.
Mm-hmm.
We could do this as well as because Estelle was supposed to speak on Thursday afternoon. You see now she's.
No, I'm not here on Thursday afternoon. I can squeeze it on Thursday morning.
Oh, you're leaving in the morning already.
I'm leaving at noon.
You're leaving during your talk.
Any question?
No,
Nope.
You're leaving. That's it. No.
I can squeeze that on Thursday morning because I have time.
We can have short. So I guess that's it, right?
There is no point of starting here, I guess, for 10 minutes.
Right. We can take the break now. Unless some people, we can just talk. Right?
If you have any question, please do ask F.Renaud tomorrow. No, I'm kidding.
It's not meant to be like a seminar.
Yeah.
We're allowed to talk to this guy.
I'm used to give seminars, so it looks like a seminar, but please talk to me.
Good question for you. Do you have your simulation of the AGN?
No.
That's the weather. I have one. Yeah. You should want to jet trying to pan it out at the time. Because people always claim, right, that once you get the AGN feedback, it could potentially make the rest of the ISM crunch because you're dumping hot gas into the cavities in the structure. You don't see that so much here. You see them getting pushed together, actually.
The denser terms.
Yeah, the dense stuff, yeah. Because
I think it's not on the density and the residuosity there.
that was my
But
first
sorry,
question.
yes, okay, but this one.
What?
Really high resolution calculation, I think.
What do you mean about they're being crushed? What's the expectation there?
Well, so the idea was that, to go to this bubble that was now hot, right?
Yes.
Around the ISM. So basically, you're feeding the bubble plane hot gas. And it then pushes back down the disk again. You can see it a little bit. It starts to push those bubbles down towards the midplane, which I'm assuming is the y-axis here, right?
Yeah.
And it pushes them back, and there was an idea pushed around that it then squeezes.
I see what you mean.
And you get a big burst of star formation.
So it has a retroaction on the you can see it fall back onto the plane.
I mean, you're adding pressure to the tenuous part of the ISM, right?
Yeah.
The low density environment, you're adding more pressure but adding more heat. So you can maybe squeeze the
Through
clouds,
this. Yes, I see.
and then get a burst of star formation. But I don't know if you really see that effect there so much actually. You obviously don't more than star formation, but I'm just saying generally. I don't see it squeezing.
I'm sure you guys have control of the shape.
No,
No, but it'd be interesting to have the mass flux or the energy flux that goes through this long. You can clearly see there's some propagation.
But that's in the light. You are just putting one.
Oh yeah, but there's a random scale. I mean, what kind of way to do it?
In this case, quite small.
Yeah, maybe it doesn't actually, it just takes longer for it to work. Yeah, maybe it just takes a long time for it to happen. But the AGN don't last for a huge amount of time, do they?
Oh gosh, you're still streaming.
Excellent.
You can say goodbye first.
Bye. See you tomorrow. Not me.
Yeah,
Who's on tonight?
nobody.
Oh, that's okay.
I think we're done.
Ah,
I think we're done for the day. It's